In this set of notes, we're going to look at different integration techniques, and it corresponds with section 7.1 of the textbook. Let's start with a motivating example. Suppose we want to calculate the following indefinite integral. Notice that we have x times e to the 1 minus 2x squared dx. Previously, our goal when working with indefinite integrals was to identify the antiderivative and work backwards. So in other words, we want a function f of x whose derivative is the following. Now this one looks a little bit more complicated than the ones that we've seen in the past, but one thing to notice is that we do have a function inside of a function. So instead of e to the x, we have e to the 1 minus 2x squared. So previously we saw that when taking the derivative of a composition function, we need to apply the chain rule. So it would stand to reason that we need to find a way to reverse the chain rule or to work backwards in order to find this integral. And so for example, what we could do is we could define the inner function to be 1 minus 2x squared, and then the outer function to be e to the x. And you might say, well, what about the x that's out front? Well, remember our goal is to find a function whose derivative is equal to x times e to the 1 minus 2x squared. And so remember, when we apply the chain rule, we're also going to have to take the derivative of the inner function. So usually when we start to work with these, when you identify the composite function, the composite piece won't be the entire function, because remember, we are going to also have to account for the derivative of the inner function. And so recall that the chain rule states the following. If g is differentiable at x and f is differentiable at y equals g of x, then the composite function f of g at x is equal to f with g of x being the inner function. And then the derivative is given by the derivative of f evaluated g of x multiplied by the derivative of g of x. So for this particular example, notice that inside the integral we have x times e to the 1 minus 2x squared. So in other words, what we are trying to find is we want to find a function that has this derivative. So let's start out with that inner and outer function that we defined earlier. So let's let our inner function be equal to 1 minus 2x squared. And then notice if we're going to apply the chain rule, we need both the derivative of f and we'll also need f. So in this particular case, since we have e to the 1 minus 2x squared, let's let f of x be equal to e to the x. And then of course we know that this is going to imply that the derivative of f of x is equal to e to the x as well. We'll also need the derivative of our inner function, or the derivative of g of x, and so in this case that would be equal to minus 4x by the power rule. So let's plug that into that derivative piece from the chain rule. So notice this is coming from right here. And if we do that, we're going to take our derivative of f of x and we're going to evaluate it at our g of x. So notice that piece is right here. We've got e to the 1 minus 2x squared. And then we need to multiply that by the derivative of g of x, so minus 4x. So again, we're just applying the chain rule here. So notice, again, by the chain rule, if we were to take, or to integrate rather, this derivative, we should get back to the original function plus c. Or, plugging in what we have up above, we have that the integral of negative 4x e to the 1 minus 2x squared dx is equal to e to the 1 minus 2x squared plus c. But notice this is not the integral that we want. This is the integral that we want. And so just as a reminder, that was what we started out with this example. But notice that these two integrals are only off by a factor of negative 1/4. So if we were to multiply both sides here by negative 1/4, notice that we would get the following. And this is exactly what we wanted. So we started off by asking, what is this integral equal to? And here we have the answer. And so this process leads us to the following rule. It's called the substitution rule for indefinite integrals. And it says that if we let u equal g of x, so in other words, we let this one be the inner function, then the integral where we have f evaluated at g of x times the derivative of g of x, and so notice this piece right here, that is the derivative from the chain rule, then we get that that is equal to the integral of f of u du, but notice that that is the same thing as the integral of f of g of x dx. So the substitution rule really is just reversing the chain rule. And so integration by substitution can be summarized into 3 different steps. The first thing we have to do is define the new variable u equals to g of x. In other words, we have to find our inner function. We then convert our integral over to x to an integral over to u. And we're going to look at several examples of this, and then we rewrite that integral so that x does not appear anywhere. And so again, we're going to look at some examples of what this looks like. So the first example we have here is we want to evaluate the integral of 4 times x to the 3 multiplied by 4 minus x to the 4th to the 3rd power. So the first thing we want to do is identify our inner function. So before we had e to something, and we use that as the inner function. Here, notice that we have 4 minus x to the 4th to the 1/3 power. Now again, whenever we work with this style problem, we're probably going to have something multiplied out front, and that's going to be related to the derivative of the inner function. So in this case, what we're going to do is we're going to try an inner function of 4 the minus x to the 4th. Now, I will say when you go to work on your book problems, the first couple are going to help you by identifying that inner function, and then later on you'll need to identify the inner function yourself. In practice, identifying the inner function may take a couple tries. It's not always going to be immediately obvious. And then so notice if our inner function is 4 minus x to the 4th, then of course the outer function is going to be x to the 1/3. All right. So first thing we're going to do is we're going to set u to be equal to 4 minus x to the 4th. And we hope to turn the integrand into a function like u to the 1/3. So the first thing we're going to do is we're going to integrate over u. So to integrate over u, we don't want to use dx, we want to use du. So in order to do that, we need to take the derivative of u with respect to x. And so again, u is equal to 4 minus x to the 4th power. So using our power rule, that's going to be equal to minus 4 times x to the 3rd. Now, we don't want to just have u, we want to move dx over to the other side so that we can make a substitution. You'll see that here in just a minute. But notice this implies that du is equal to negative 4x cubed dx. So we could rewrite our integral. So we had the integral of 4x cubed times 4 minus x to the 4th all to the 1/3 power dx. And now we're going to make some substitutions. Now the first thing we're going to do is notice here inside the inner function we've got 4 minus x to the 4th. We know that is what u is equal to. So I'm going to have u to the 1/3. Next, I need to account for, I have both the dx and the 4x to the cube. Notice here that du is equal to minus 4x to the cube dx. So here, I just need to have du, and I'm going to put a minus out front, because again, here we have minus 4x cubed dx instead of 4x cubed dx. Now we can take the integral. Here we have u to the minus 1/3 du. So this is very similar to the problems that we've seen before, and we're going to use that reverse power rule. and this is equal to minus 3/4 u to the 4/3. And then as we've seen before, we do need to add on to that constant because with, really we have a whole family of antiderivatives here. Next, if we want this back in terms of x, we can substitute back in what u is equal to. So we'd have minus 3/4 4 minus x to the 4th, the 4/3 plus c. Now, especially at this stage, I highly recommend that any time that you compute the integral, take the derivative of that integral to see if you get back to the original function. And so this is always a really good check to perform, especially as you're getting used to the different integral rules. So for our check here, we're going to take the derivative with respect to x of minus 3/4, 4 minus x to the 4th, 4/3 plus c. And we're going to apply the chain rule, keeping in mind that the derivative with respect to x of c, since c is a constant, is just going to be 0. So applying the chain rule to the first term, we're going to have negative 3/4 times 4/3 times 4 minus x to the 4th to the 1/3 times minus 4 x to the 3rd. And again, that is by application of the chain rule. And notice this is equal to 4 x to the 3rd times 4 minus x to the 4th to the 1/3 power. And that is our original function, so that checks out. Okay. And I do want to make sure, notice I don't put an equal sign there. These are two separate lines. All right, so let's look at another example. So next, we're going to evaluate the indefinite integral of x plus 1 divided by 5 minus x dx. Now, this one is a little bit harder to identify that inner and that outer function. So one thing to keep in mind is we're looking for that function whose derivative is equal to this. So notice we have something in the denominator. This isn't something that we could split up into two separate fractions. And so we'll want to keep the derivative of the log in mind here. So remember, the derivative of the natural log of x is equal to 1 over x. And so it would be good here if we could have the inner function be 5 minus x, keeping in mind that that's going to help us because, again, the derivative of the natural log of x is 1 over x. So we're going to set u to be equal to 5 minus x. And again, we hope to find the integram of a function like 1 over u. So to integrate over u, we need to take the derivative of x, upper derivative of u with respect to x rather. And to notice here, that's just going to be equal to -1. And so this suggests that du is equal to negative dx. Right? So looking up here, if we want to try to make a substitution, just kind of making some scratch marks here off to the side, notice if I were to have the integrand or the integral of 1 over 5 minus x, or in other words, 1 over u, I would still be left with an x plus 1 up in the numerator. And since the derivative of u with respect to x is only -1, I'm not going to be able to account for that extra x plus 1 with the derivative of the inner function. But what I can do is we can notice that since u is equal to 5 minus x, that this is going to imply that 5 minus u is equal to x. And remember, that extra thing that we have up top is going to be x plus 1. So therefore, we could rewrite x plus 1 as 6 minus u. So starting out with our original integral, we've got x plus 1 over 5 minus x dx. And now we're going to go through and make our substitutions. So x plus 1 is equal to 6 minus u. And 5 minus x is equal to u. And then we have that dx is equal to minus du, so we have the following. Now looking at this, notice that we still have a u in the denominator, but this integral is easier to work with because we can actually break this into two fractions. Notice that this is equal to 6 over u plus u over u du. This should be a minus u over u du. And so here we can break up that integral. And so notice here we're going to have the integral of u over u du, which is just 1 du, minus the integral of 6 over u du. And so this is going to be equal to u for the first integral, minus 6 times the natural log of the absolute value of u plus c. Now if we want in terms of x, we can make the substitution. U is equal to 5 minus x. And so this becomes 5 minus x minus 6 times the natural log of the absolute value of 5 minus x plus c. And again, when you first start working with these, it may take some trial and error to identify what the inner function should be. All right, working with definite integrals is going to be similar to working with indefinite integrals. Recall that part 2 of the fundamental theorem of calculus says that to evaluate a definite integral, we must find an antiderivative of the integrand and then evaluate the antiderivative at the limits of integration. When we use the substitution u equals g of x to find the antiderivative of the integrand, the antiderivative will be given in terms of u at first. So to complete the calculation, we proceed with either of the two ways. We can leave the antiderivative in terms of u and change the limits of integration according to u equals g of x, or we can write the antiderivative as a function of x by substituting in u equals g of x and then evaluate the antiderivative at the limits of integration in terms of x. Now this second one, this is pretty much what we've been doing in the past two examples. So notice as a very last step in both this example and the one up here, we rewrote the integral in terms of x. Well, the solution in terms of x. And so if we were to have a definite integral, once we rewrite this in terms of x, then we could evaluate that definite integral in terms of the original limits of the integration. But we're going to look at examples of both of these. And so the first way, which we haven't seen yet, is summarized by the following. And so notice again, we're still applying the chain rule just like we saw before. The only difference actually comes here to here. And so for example, if on your original integral you had 0 to 1, when you rewrite it in terms of u, you'll evaluate g at both 0 and 1, and that will be what you write at the bottom and the top of the integral. And so in practice, this means that we add a fourth step to those three steps that we just saw earlier, and here is that fourth step. And we are going to look at some examples of this. All right, so the first example that we have here is we have the definite integral from 0 to 2 of x to the 5th, x cubed plus 2 dx. And so regardless of which method we end up using, we're really going to complete those first three steps from the indefinite integral first. And so typically you won't work the indefinite integral and then go to the definite integral, but I am going to do that here just for illustration. So notice here, this is very similar to that first example. Now in that first example, our outer function was going to be u to the 1/3. Here we have it to the 1/2, but we're going to work this very similarly. So we're going to start out by setting our inner function u to be equal to x cubed plus 2. Notice that if we were to take the derivative here, that d of u with respect to x is going to be equal to 3x squared, or we would say that du is equal to 3x squared dx. And so let's start with that indefinite integral. All right, so starting with the indefinite integral, we would have x to the fifth times the square root of x cubed plus 2 dx. So we're going to make our substitutions here. So we're going to have the integral. We'll start with that composition function first. So notice we have the square root of x cubed plus 2. Well, notice that is just going to be the square root of u. Now, our other piece we have here is x to the fifth. And notice if we look at the derivative of u, we have 3x squared dx. So we don't have x to the fifth. So let's rewrite this as the following. We know that we're going to need an x squared. So notice that this is equal to x to the third times x squared times the square root of x cubed plus 2 dx. That gets us a little bit closer to something that we want, but notice that we also have a 3 out front. So let's multiply this by 1/3 times 3. So if we write it this way, now notice that in order to get our du that we want, du is equal to 3x squared dx. So that will take care of these 3 pieces, but that still leaves me with a 1/3 x cubed. So I can move the 1/3 out here, but if I want to know what x cubed is equal to, notice that x cubed is equal to u minus 2, since u is equal to x cubed plus 2. So here out front, we could have a u minus 2, and we've substituted all of our pieces. Now to make this easier for me to actually work with the integral, I'm going to go ahead and multiply through by that u minus 2. So first I'm going to have u times the square root of u, which is going to be u to the 3/2 power, minus 2 times u to the 1/2. Now from here, I know since I have a sum, I can then have the sum of the integrals, and I can use the reverse power rule. So here I'm going to end up with 1/3 times 2/5 u to the 5/2 minus 4/3 u to the 3/2 plus c. And so now that I've got the indefinite integral, we could look at the 2 different ways that we could solve the definite integral. So the first method would do the following. So we start out with our definite integral that we want to find. So we have 0 to 2, x to the 5th times the square root of x cubed plus 2 dx. And we already know that this is equal to 1/3 times the integral of u to the 3/2 minus 2 u 1/2 du, but the piece that we need to worry about is what goes at the bottom and the top of the integrand. So what we do is we evaluate g of x at both 0 and 2. So in this case, u is equal to x to the cube plus 2. So evaluating at 0, we're going to have 2, and evaluating at 2, we are going to have 10. So since we already solved the indefinite integral, we know that this is equal to 1/3, 2/5 u to the 5/2 minus 4/3 u to the 3/2. And now we're going to evaluate this from 2 to 10. And remember that we saw this notation just briefly in the last set of notes, and really what this means is we're going to substitute 10 in for u, and then we're also going to substitute in 2 for u, and we're going to subtract off the substitution with 2 from the substitution with 10. And so in other words, this is going to become the following. We're going to have 1/3 times 2/5, 10 to the 5/2, minus 4/3, 10 to the 3/2, minus 1/3 times 2/5 times 2 to the 5/2, minus 4/3 times 2 to the 3/2. Right? The other method, and of course you would want to simplify this. And if you simplify it, you would find that this is equal to 16 over 45 times the square root of 2 plus 25 times the square root of 10. For the sake of time in this video, I'm not going to do that. But we do want to go ahead and see what the other option is. So method 2, what we would do is, so here what we did was we substituted in for the lower and the upper bound. The other thing that we could do is, again, starting with that indefinite integral where we had x to the 5th, the square root of x cubed plus 2 dx, and we found that that was equal to the indefinite integral. Oh, pardon, that was equal to, not the indefinite integral, but that was equal to 1/3 2/5 u to the 5/2 minus 4/3 u to the 3/2. Well, from here, we could substitute in what u is equal to. And so notice it's going to be equal to 1/3 2/5. And remember that u all the way up at the top was equal to x cubed minus, x cubed plus 2. To the 5/2 minus 4/3 x cubed plus 2, again substituting in what u is, to the 3/2. And then, sorry, I've kind of got this going up and to the right. What we would do is, now that this is in terms of x, we would evaluate at our original limits from 0 to 2. And so this would end up being 1/3 times 2/5. And notice inside here, for the first one, we're going to have 2 cubed plus 2, which is 10 to the 5/5, minus 4/3 times, again, if we evaluated it at 2, we're going to have 2 cubed plus 2, which is 10 to the 3/2, minus 1/3 times 2/5. Well, here I'm going to have 0 plus 2, so I'm going to have 2 to the 5/5 minus 4/3. Again, when I substitute in that 0 for x cubed, I'm going to have 0, so that's going to become a 2 to the 3/2. And we can see that whether we use method 1 or we use method 2, before simplifying and then of course after simplifying, but we can see that before simplifying we end up with the same thing no matter which of those two methods you use. So either one is completely fine. So let's look at one more example. So we have one more example. In this example, we're going to look at the integral of e to the x divided by e to the x plus 1 squared dx. And then our lower bound is the natural log of 4, and our upper is the natural log of 7. So here, we're going to set our inner function to be u is equal to e to the x plus 1. Notice here that the derivative of u with respect to x is equal to e to the x, which suggests that du is equal to e to the x dx. We're going to use method 1 for this example. So starting out, here is our original integral. So let's go through and make our substitutions. So in the denominator, we have e to the x plus 1 squared. Well, u is equal to the e to the x plus 1, so in the denominator we have u squared. And the numerator we have e to the x dx, but notice that du is equal to e to the x dx. So we have the following. Now for our upper and lower bounds, we don't want to have the natural log of 4. Now that we have this in terms of u, what we want to do is substitute in x for the natural log of 4. So notice if we have e to the natural log of 4 plus 1, that's going to be equal to 4 plus 1, which is 5. And if we have e to the natural log of 7 plus 1, that's going to be 7 plus 1, which is 8. To make this a little bit easier on myself, I'm just going to write this as the following. There should not be a negative sign there, that's just 1 over u squared. And now I can apply that reverse power rule that we have seen before. And so this is going to become minus u to the minus 1. And we're going to evaluate it from 5 to 8. So this is going to be equal to negative 1/8 minus negative 1/5, which is equal to negative 5 over 40 plus 8 over 40, which is equal to 3 over 40. Your book has lots more examples on the substitution rule as well as how to identify that inner function. So as always, I highly recommend also going through all of the book problems. And as always, if you have any questions, please let me know.